Let me tell you something strange about your mind. Right now, as you sit there watching this, your brain is quietly running simulations of lives you never lived. Maybe a tiny voice asks, what if I had taken that other job? What if I had said yes instead of no? What if I had stayed instead of leaving? Your mind keeps opening doors that were never walked through. And the funny thing is, you cannot stop it. You can distract yourself with work, with music, with conversation, but sooner or later, your brain sneaks back into that strange little laboratory where it experiments with alternate versions of reality. Now, that's a curious thing. Why would evolution give us a brain that constantly wonders about things that never happened? Why waste energy imagining possibilities that are already gone? Well, today I want to show you something fascinating. That strange habit your mind has, that endless stream of what-ifs, may not be a flaw at all. In fact,
It might be doing exactly what the universe itself does.
and to understand why, we have to start with something extremely simple.
A coin.
Yes, just a coin. Let's imagine I flip a coin into the air, heads or tails.
Before it lands, what is it at?
Most people say, well, it's going to be one or the other, we just don't know which yet. That seems reasonable. The coin is already determined, we assume, the outcome is fixed, we just lack the information. But let me push that idea a little bit, because the deeper you look, the stranger it gets. When you flip a coin, your thumb pushes upward. The coin spins rapidly. As it rises, it rotates through the air, wobbling slightly. Tiny currents of air swirl around it.
Maybe the room ventilation nudges it a little.
Maybe someone walked by and disturbed the air pressure. Maybe the coin's edge hits your palm at a slightly different angle when you catch it.
Every one of these details matters.
In principle, if you knew exactly how hard your thumb pushed,
Exactly how fast the coin spun?
exactly how every air molecule moved, you could calculate the result, heads or tails, perfectly. This idea that the universe is completely predictable was once extremely popular. Physicists in the 18th and 19th centuries imagined something extraordinary. They imagined an intelligence so powerful, so perfectly informed, that it knew the position and velocity of every particle in the universe. Such an intelligence, they believed, could predict the future with absolute certainty. The entire universe would be like a giant clock, tick, tick, tick.
Everything determined by the previous moment. No surprises?
No uncertainty, no real what if, just the inevitable unfolding of cause and effect. It's a beautiful idea. And for many everyday situations, it works beautifully. And you can predict where a baseball will land. You can calculate how a bridge holds weight. You can send rockets to the moon. All of that relies on the assumption that the universe behaves predictably.
But then something happened.
Something physicists did not expect. When we began looking at very small things, atoms, electrons, particles of light, the clockwork universe started to break. At first we thought we simply needed better instruments, better measurements, more precise experiments. But the deeper we looked,
The more it seemed that the randomness was not caused by ignorance. It was built into nature itself.
let me give you an example. Take a radioactive atom.
Some atoms are unstable.
Eventually they decay. They spit out a particle and transform into a different element.
The question is simple. When will it decay? Tomorrow? Next year?
In 10,000 years?
Here's the astonishing answer.
No one knows. And
Not because our instruments are bad.
not because we lack information, but because the universe itself does not decide until the moment happens. You can take 1,000,000 identical atoms, perfectly identical. Same environment, same temperature, same everything, and they will decay at completely different times. One now, one later, one much later.
There is no hidden clock ticking inside them.
All we can predict is probability. For example, we might say, in the next 1,000 years, half of these atoms will decay. That's called the half-life. But which half? Nobody knows. Nature rolls the dice.
Now that idea made some physicists very uncomfortable.
In particular, a certain gentleman you may have heard of,
Albert Einstein.
Einstein believed deeply that the universe must be orderly and deterministic underneath.
He once famously said, God does not play dice with the universe. He was convinced that randomness was just a temporary illusion, a gap in our knowledge. Surely, he thought, there must be some hidden mechanism underneath quantum mechanics, some deeper layer we simply hadn't discovered yet. And Einstein was no fool.
When Einstein disagreed with a theory, he didn't just complain.
He built brilliant thought experiments. He challenged quantum mechanics again and again.
For decades. But every experiment, every test, every clever challenge
kept confirming the same strange conclusion. Nature really does appear to play dice.
But here's the subtlety.
When physicists say the universe is random, we do not mean chaos. Randomness does not mean anything can happen.
The dice are not wild.
They are loaded, very precisely loaded. The probabilities follow strict mathematical laws. And this brings us to something very beautiful. Randomness, when you study it carefully, produces patterns. Let me show you. Imagine a very drunk man leaving a bar. He's standing next to a lamppost. He wants to walk home. But he's so drunk that each step he takes is completely random. Sometimes he steps left,
Sometimes right.
sometimes forward, sometimes backward. Let's simplify things. Suppose every step he flips a mental coin. Heads, step right. Tails, step left. One step at a time. Completely random. Now here's an interesting question. After 100 steps, where will he be? You might think the answer is simple, but it's not. On average, he'll still be right near the lamp post. Half his steps go one way, half the other.
But if you ask a different question,
How far away is he likely to be? Now something remarkable appears. The distance grows slowly, not proportional to the number of steps, but proportional to the square root of the number of steps. And
That means after 100 random steps, he's probably about 10 steps away.
after 10,000 steps, maybe about 100 steps away,
random wandering still gets you somewhere, just very inefficiently. This process, called a random walk, turns out to be everywhere in nature. Smoke particles drifting in air, perfume spreading across a room, heat moving through metal, stock prices fluctuating in markets, even the movement of molecules inside your body. All of these follow random walks. The universe is full of tiny wandering steps, and yet from those random steps, larger patterns emerge. Temperature, pressure, diffusion. Entire fields of science are built on these patterns. Now, here's where things start to get truly fascinating, because when we look at the quantum world, randomness behaves in an even stranger way. In the everyday world, possibilities exist only in our imagination.
But in quantum mechanics,
Possibilities seem to exist in reality. Let me explain what I mean.
imagine a particle of light.
A photon, you send it from point A to point B. In the ordinary picture, the photon simply travels in a straight line, the shortest path.
nice and simple.
But quantum mechanics tells us something extraordinary.
The photon does not take just one path.
It takes every possible path, every one. It goes straight,
It curves.
it zigzags, it loops around, it takes absurd detours. Mathematically speaking, it explores every possible route between A and B. Now, I know what you're thinking.
That sounds ridiculous.
How can a particle take all paths at once? Well, physicists ask the same question. And the strange answer is because when you add up all those possibilities together,
Something remarkable happens.
Most of the paths cancel each other out.
but the paths close to the straight line reinforce one another. The result? The particle behaves as if it traveled along the straight path. But underneath, every possibility contributed. Nature didn't choose the path first. Nature explored all possibilities simultaneously, and the final outcome emerged from their interference. This idea, called the sum over histories, is one of the most beautiful ways to understand quantum physics. Instead of deciding one path, the universe briefly considers them all. Now think about that for a moment. Your brain does something very similar.
When you wonder,
What if I had taken that job? What if I had moved to another city? What if I had said something different? Your mind is exploring alternate histories. Paths that could have happened, most of them fade away. But a few possibilities remain meaningful.
they shape how you understand your life.
Your choices, your luck, your future.
And in a strange, poetic sense,
Your brain might be imitating the way nature itself explores possibilities. But if you think that's strange,
Wait until you see the experiment that completely shattered our understanding of reality.
an experiment so bizarre that I once said it contains the only real mystery of quantum mechanics. It's called the double slit experiment. And what it reveals about reality is even stranger than randomness. Now let's return to that strange little experiment I mentioned a moment ago. The one that seems simple on the surface but ends up shaking the foundations of how we think about reality. Imagine you have a wall with two narrow openings cut into it. These openings are called slits. Behind the wall is a screen that records where particles land. Now suppose we fire tiny particles, electrons for example, toward the wall. If electrons behaved like little billiard balls, you would expect something very straightforward to happen. Some electrons would pass through the left slit and hit the screen behind it. Others would pass through the right slit and hit the screen behind that one. In the end, you'd see two bright bands forming on the screen, each one corresponding to one of the slits. That's exactly what would happen if you threw baseballs through two doorways. Half the baseballs go through one door, half through the other, and they pile up behind each doorway. Simple, clean, predictable. But electrons, those tiny little bits of matter that make up atoms, refuse to behave so politely. When physicists first performed this experiment with electrons, they did not see two piles forming on the screen. Instead, they saw a pattern of many bright and dark stripes spreading across the entire surface. Bright band, dark band, bright band again, like ripples on water. And that pattern is something we normally associate with waves. If you drop two stones into a pond, the ripples from each stone spread outward and overlap. Where the crests of two ripples meet, the water rises higher. Where a crest meets a trough, they cancel each other out and the water becomes calm. This overlapping creates a pattern, peaks and valleys across the surface. That's exactly the same pattern the electrons create. Now hold on a second, because this is where things get truly bizarre. At first, someone might say, well, maybe the electrons are interfering with each other like waves. That sounds reasonable if you imagine many electrons traveling together in a beam. But then physicists tried something even more careful. They slowed the experiment down until only one electron passed through the slits at a time. One electron, wait a moment, another electron, wait again. Each electron traveling completely alone with no other electrons nearby to interact with. You might expect that the interference pattern would disappear because there is nothing for the electron to interfere with. But it doesn't disappear. The pattern still builds up gradually on the screen, dot by dot, as each lone electron arrives. Each electron lands at a specific location, but after thousands of them arrive, the same ripple-like interference pattern appears. Somehow, each individual electron behaves as if it passed through both slits at once and interfered with itself. That's the conclusion the mathematics forces upon us. The electron does not simply choose one slit or the other like a tiny bullet. Instead, it behaves like a wave that spreads out and explores both paths simultaneously. Those possibilities overlap and interfere before the electron finally lands somewhere on the screen. It is as if the electron asks itself a what-if question. What if I go through the left slit? What if I go through the right slit? And the final result emerges from the combination of both possibilities. Now, naturally, when physicists saw this, they said, fine, but let's watch it more carefully. Suppose we place a tiny detector near the slits to see which one the electron actually passes through. Maybe the electron really does go through only one slit, and the strange pattern is just some hidden effect we don't understand yet. So we install a little measuring device near the openings, a device that tells us whether the electron passes through the left slit or the right slit. And when we do that, something remarkable happens. The interference pattern disappears completely. Instead of many bright and dark stripes, the screen now shows two simple bands, exactly what we would expect from little particles going through one slit or the other. The mere act of measuring which path the electron takes changes the outcome of the experiment. Let me repeat that because it's so extraordinary. When we do not measure the path, the electron behaves like a wave passing through both slits. When we measure the path, the electron behaves like a particle passing through one slit. The universe seems to keep multiple possibilities alive until information about the path becomes available. Once that information exists, the possibilities collapse into a single history. It's not that the electron changes its mind or that our curiosity magically alters reality. Rather, the laws of quantum mechanics say that when a system becomes entangled with the measuring device, when information about the path leaks into the environment, the interference between possibilities disappears. The possibilities stop overlapping and start behaving like separate classical alternatives. In other words, the universe allows many potential histories to coexist. But the moment the world records which history occurred, the others fade away. Now, if you sit quietly with that idea for a moment, it leads to some very deep reflections about how nature works. For centuries, we assumed that the universe simply followed a single definite path through time, like a train running along fixed tracks. But the quantum picture suggests something richer. Before a measurement occurs, the world may not be confined to just one path. Instead, it contains a cloud of possibilities, each one contributing a little piece to the final outcome. The world explores those possibilities in a mathematical sense, and the probabilities we observe are the result of their interference. It's a bit like music. When many sound waves overlap, some notes reinforce each other while others cancel out. The melody you hear is the result of that complex interaction. Quantum events behave similarly. Each possible history contributes an amplitude, a tiny rotating arrow in the mathematics, and when you add all those arrows together, some cancel and some combine, leaving the final probability. The paths near the classical route reinforce each other, while the wildly improbable paths cancel away. That is why everyday objects seem to follow smooth, predictable trajectories, even though underneath the quantum world is exploring countless alternatives. But here is the truly fascinating connection to the way your own mind works. When you think about your past and ask, what if? Your brain is doing something strikingly similar to a probability calculation. You're exploring alternate histories of your life. What if I had chosen another city? What if I had met different people? What if I had taken a different opportunity? Most of those imagined histories fade away quickly because they don't align with reality. But a few possibilities remain meaningful. They teach you something about chance, about consequences, about the fragile chain of events that produce the present moment. In that sense, your brain is not wasting time when it contemplates alternative outcomes. It's mapping the landscape of possibility, trying to understand which events were inevitable and which were accidents of circumstance. The same reasoning appears throughout science. In thermodynamics, we analyze countless possible motions of molecules to predict temperature and pressure. In evolution, we consider the many genetic mutations that might occur and the probabilities that shape populations. In finance, analysts study the random fluctuations of markets to understand long-term trends. Again and again, we see the same pattern. Individual events are unpredictable, yet large collections of possibilities produce reliable statistical laws. The universe seems to balance between determinism and randomness, between strict rules and open outcomes. That balance is what allows complexity to exist. If everything were perfectly predictable, the world would be dull and mechanical. Every event predetermined from the beginning of time. If everything were pure chaos, nothing stable could ever form. No atoms, no stars, no life. But the real universe sits in the middle, governed by precise laws, yet open to multiple possibilities at every step. And perhaps that is why the what-if question feels so natural to us. Our minds evolved in a universe where outcomes are never fully guaranteed, where chance and necessity intertwine. Thinking about alternate futures helps us prepare for uncertainty. Thinking about alternate pasts helps us understand how fragile the present really is. A tiny change, a different meeting, a missed train, a different decision might have nudged life onto another path entirely. When you see the world that way, you begin to appreciate something profound. The reality you experience is just one thread in a vast web of possibilities that once existed, and the deeper we look into physics, the more it seems that nature herself explores that web before choosing the outcome we observe. So by now you may be feeling a little uneasy about the picture we've built. On the one hand, the universe seems to follow precise mathematical laws. On the other hand, the outcomes of individual events appear genuinely uncertain. A radioactive atom might decay now or thousands of years later. An electron might land here or there on the screen. A photon might arrive by one path or another. The laws don't tell us the exact result of a single event. They only tell us the probabilities, and that makes many people uncomfortable. They want the universe to behave like a perfectly programmed machine where every outcome is inevitable. But the more carefully physicists study nature, the more it appears that probability is not a temporary placeholder for ignorance. It's woven into the fabric of reality itself. Now here's the beautiful twist in the story. Even though individual events are uncertain, large collections of events behave with astonishing regularity. Think about flipping a coin again. One flip is unpredictable. Two flips are still uncertain. But if you flip the coin 10,000 times, the percentage of heads will hover very close to 50%. The randomness of each toss does not destroy order. It actually produces a new kind of order, a statistical order. The more events you add together, the more stable the averages become. This idea lies at the heart of thermodynamics, the branch of physics that explains heat, temperature, and energy. A glass of air in front of you contains something like 10 trillion molecules flying around randomly, colliding with each other billions of times per second. If you tried to track the path of even a single molecule, the problem would be hopelessly complicated. Yet the air still has a precise temperature and pressure that we can measure with great accuracy. How is that possible? Because when you average the behavior of enormous numbers of random particles, the chaos smooths out into predictable patterns. In other words, randomness at the microscopic level can produce reliability at the macroscopic level. This is why weather can be unpredictable day to day, yet climate patterns exist over decades. It's why individual stock trades fluctuate wildly, yet markets show statistical trends. It's why insurance companies can function even though they cannot predict exactly which person will get into an accident. The mathematics of probability reveals that randomness is not the enemy of order. It is often the source of it. And when you understand that, the idea of chance begins to look less like chaos and more like a subtle balancing act between freedom and constraint. The laws of physics set the rules, but within those rules, multiple outcomes remain possible. It's a bit like a game of chess. The rules determine how each piece moves, yet the game can unfold in millions of different ways. Nature plays by strict rules, but the results still contain an element of openness. Now think about your own life again. Every moment in your past was shaped by countless tiny events, conversations you had, opportunities you noticed, random encounters with people, even accidents of timing that nobody could have predicted. If just one of those details had changed slightly, your path might have diverged into an entirely different direction. Perhaps you would have met different friends, studied a different subject, moved to a different place. The fact that you can imagine these alternate paths is not merely a psychological quirk. It reflects the probabilistic nature of the world you live in. Your brain is constantly building models of possibilities, trying to understand which events were stable and which depended on fragile coincidences. That process helps you learn. It helps you make decisions about the future. When you ask, what if, you are not rewriting history. You are exploring the landscape of probability that surrounds every choice. And from the perspective of physics, that landscape is real in a certain sense. Before an event occurs, multiple outcomes are genuinely possible, each with its own probability. The universe does not always commit to a single path until the moment the event happens. So your mind, wandering through hypothetical scenarios, is doing something quite natural. It's trying to grasp the structure of uncertainty that shapes the world. But here's the important part, and it's the part people often forget when they get stuck worrying about their past. Exploring possibilities can teach you something, but living in them forever is like staring at the map instead of walking the road. Physics tells us that once an event has occurred, the universe moves forward along that branch of history. The probabilities that once surrounded the moment collapse into the single outcome we observe. That doesn't mean the alternatives were meaningless. They were part of the process that led to the present, but they no longer control what happens next. And that realization can be surprisingly liberating. Think again about the random walk of the drunken fellow leaving the lamppost. Each step he takes could go left or right, forward or backward. At the beginning, there are many possible paths he might wander, but once he actually takes a step, the next moment begins from that new position. The previous possibilities vanish, replaced by a fresh set of possibilities ahead. Life works the same way. At every moment, there are many directions you could move, yet once the step is taken, The future unfolds from there. The past becomes fixed, not because it was predetermined, but because the branching possibilities have resolved into a single history. And this is where the lesson of physics meets the lesson of living. The world is not a rigid machine that forces every outcome, nor is it pure chaos where nothing makes sense. It's a probabilistic universe, structured, lawful, but open to multiple possibilities at every stage. Your thoughts about alternate pasts are echoes of that openness. They remind you that chance plays a role in everything from the motion of atoms to the events of your own life, but they also remind you of something hopeful. If the future contains probabilities rather than certainties, then it also contains opportunities. New paths can still emerge. The same randomness that once created the twists in your past is also the source of creativity in the universe. The reason stars form, species evolve, and ideas appear in human minds. The universe experiments continuously, exploring possibilities through the language of probability. And perhaps the most remarkable thing is that we, little arrangements of atoms walking around on a small planet, are able to understand that process at all. We can write equations that describe the dance of particles. We can build experiments that reveal the hidden patterns of chance. We can even reflect on our own decisions and wonder how probability shaped them. To me, that is one of the most beautiful aspects of science. It shows that the curiosity inside your mind is not separate from nature. It's a continuation of the same exploratory spirit that exists in the quantum world itself. The universe asks, "What if?" in its own mathematical way, and your brain asks, "What if?" in thoughts and imagination. Both are attempts to understand possibility. So the next time your mind drifts into one of those alternate histories, wondering how life might have been different, remember that you are glimpsing the probabilistic structure of reality, but also remember that the most interesting probabilities are the ones still ahead of you. The universe has not finished rolling its dice yet, and neither have you.